We're going to be doing problem 12-35 from section or chapter 12, and now we're doing curvilinear motion with in cylindrical coordinates. So this was we begin to see a drop off in student activity because it gets pretty hard after this, right? But remember, chapter 12 is crucial for chapters 13 through 16, or however many chapters your professor will cover. Some things I want to go over here is, before we get started, is you might be noticing in some problems why sometimes R doesn't change, and then let's say you're moving in a circle, right? You have a particle here, right? And in this case, let's assume this is a circle, okay? I know my door is not really a circle, but let's say they're telling you that it's 5 meters, right? And then when we take the time derivative of R, right? Let's just, 5 meters. When we take the time derivative of that, right, it's just constant because it's going around a circle with constant radius. All right, so R dot and R double dot will be 0. Okay, when we take time derivatives of a constant. Okay. And then you might be noticing that in this problem, for example, they give you R varies with the angle, which makes sense, right? Because we can see from this photo or this picture that, at this instant, okay, let's use red. So at this instant, this is R, but, at this instant, right, it's going to be R prime. Right, so it's going to be larger, right? And when we get all the way up here, right, once the particle is all the way over here, and your weird rod, which you're going to see the weirdest figures in this book. Once it's over here, right, R, let's call it R double dot, or R double prime, it's going to be even larger, right? And that's because theta is increasing, right? Keeps getting bigger and bigger, or I guess R theta double dot or theta double prime, right? So that's essentially why in some problems we have a varying R, and in other problems we just have a constant R. So if you're traveling in a perfect circle, R double dot and R dot are going to be 0. Okay, so peg P is driven by the fork length OA, right? Driven by OA along the curved path described by R2 theta, right? And then we're going to be using radians here, okay? At the instant, theta equals pi over 4, which is 45 degrees. The angular velocity and angular acceleration of the link are theta dot and theta double dot. Right? If you're a physics major, you might have seen theta dot as omega, right, angular velocity, and theta double dot as alpha. Okay. So if that helps you understand these, dot notation a little better, feel free to just change them up. But I would say just try to stick with the book's notation. Okay. Because your TA might not necessarily understand what you're doing, and they're like, what is he doing? And then they'll just mark it off. Okay, so let's start with so we're trying to find the magnitude of the peg's acceleration at this instant. Okay, so at the instant of theta pi over 4 rads. Okay, and remember, radians is kind of like a pseudo unit. So we still leave everything in feet per second and feet per second squared. So R2 theta. Okay. So if I take one time derivative with respect to, we're going to be using the chain rule a lot for these problems, right? Because we're taking a time derivative of something with respect to t, but there's no t inside your function, right? So you're going to have to use handy dandy. So this will be, let's say dr d theta d theta dt. Okay, so we know r is, so r dot is dr dt, and then r double dot is dt squared. Okay, so we can write we can use the chain rule here just like this, right? And we know that dr d theta, right? That's, you know, we're going to be able to take a one derivative with respect to theta for this equation, and then d theta dt is just theta dot. Okay, so let's kind of giving you guys a brief rundown of a lot of things right now. So theta double dot is theta dot d theta dt, and then theta dot, and then theta double dot is dt squared, right? Velocity, acceleration, velocity, acceleration. Okay, and then some equations that we'll be using here are going to be my radial component of acceleration, which is r double dot minus r theta squared, and then your angular acceleration component is r theta double dot plus 2r dot theta dot. Okay, I don't think you have to memorize these, but you know, if you can, might as well, but if not, just put them on a cheat sheet. Alright, so let's go back to the problem. So r dot, we need to do one chain rule, or apply a chain rule here, and then we get dr d theta is just 2, and then d theta dt is just theta dot. Okay, so that's r dot. And then r double dot is going to be one time derivative of this again, and we essentially just get 2 theta double dot. Okay, luckily for us, they give us theta dot at pi over 4 and theta double dot at pi over 4, right? So we can just easily get what the velocity is, transverse velocity. So it's 2 theta dot, so it's 2 times 3, so 6 feet per second, and then 2 times 1, right? So 2 feet per second squared. Okay, so we have r dot and r double dot, and we have theta dot and theta double dot. So now we can just plug it into this equation over here, or these two equations. Let's switch colors. So let's do the radial component. It's going to be r double dot, so that's 2 minus r, so what's r? Oh, it's 2 theta, so let's calculate that. 2 times theta, so it's 2 times pi over 4. 2 times pi over 4, which is just pi over 2. Okay, so that's 2 minus pi over 2, right? So that's r, and then theta dot squared. Where are you, theta dot squared? So that's going to be 3 squared. Okay, so that gives us 2 minus pi over 2 times 9. Okay, and so let's see. So plugging that into a calculator. So if you guys don't have a graphic calculator, I've been using this Desmos calculator, which is fantastic. It lets you go back to you know, the previous answers and stuff like that. So very useful. So when you do this, we end up getting minus 12.137 feet per second squared, and then a theta, and then we get where are you? So a theta, so angular component is going to be r, so pi over 4, pi over 2, times theta double dot is just 1, right, plus 2 times r dot, which is 6, and then our theta dot. Where are you, theta dot? So that's 3. Okay, and then this gives us 37.57 feet per second squared. And to finalize it, to get the magnitude of the peg's acceleration at this instant in time, we get a magnitude, 12.137 squared plus 37.57 squared. Okay, and then I wonder if I did this here. Probably not. No, I did not. But yeah, overall, yeah. So once you plug this into your calculator, you should get, I don't know, 400. This is, let's say 40. I don't know. Let's say approximately 40. But just kidding. Just do this on your calculator and then you should get your final answer. I'm just going to leave it like this. I don't want to lead you guys astray. But yes, so overall, have these equations written down in the corner of your notebook somewhere easily accessible, right? And then just tackle it how we approached it. The first thing we did was individually calculate what each and every one of these terms. And then the last thing we did was just plug it into those 2 equations. All right, and then we got our answer pretty easily that way. All right, hope this video helps, guys. Don't forget to subscribe. I'm hoping to keep updating chapter 12 as the weeks go on. Hopefully we get to chapter 13 soon, so keep you guys posted. Thanks a lot, guys. Bye.